that line of sentence. That's what you did wrong. Oh, it's not a technical measure to want to rate, but right, which is fair, and I just, my thing is, I have like, this is like
Okay, I'm going to introduce you, okay?
Sick.
You ready?
I am.
You're set. This is a pen. It works. Here's your lecture. Here's your lecture notes printed out. If you'd
Perfect.
rather use DocuCam, you totally can, but, you know.
This works.
I'm going to sit right there. I'll be here if you need me. The tablet's set up. He can use DocuCam if he wants, printed out the notes.
Just want to make sure this thing was set up. With,
This thing?
No, that.
That's all. That? Oh yeah, that's all set up. This is my tablet. I just hooked up like I normally do.
It's already displaying, I think.
Okay,
We're good.
that's what I was checking.
Yeah.
Because I have to switch it.
Oh, got it. Okay. Yeah. All right, everyone, let's get started. How's everyone doing? Yeah? Okay. Today, this first lecture, we're going to learn about a new type of heat exchanger analysis. So we learned about something called the log mean temperature difference, or LMTD. I didn't call it that specifically in our last lecture, but that's what you learned. And today you're going to learn something new called the NTU Method. And they're essentially equivalent, so you can kind of pick which one you like more to solve problems for you today. And this first lecture is going to be given by one of our CAs, a Sheesh, and then I'll come back and do the second lecture. So Sheesh is really interested in possibly teaching in the future, so this will be good practice for him to kind of, get exposure to lecturing to a big classroom. So please, stick with him and be engaged and answer questions. And at the end, the participation question will actually be a free response question where you give him some constructive criticism and also say something that you liked about his lecture. And then we'll go through and manually, as Sheesh looks at those, go through and give you a point if you said anything. Okay? Yeah, so with that, I think we'll get started, and then I'll pick back up in The next lecture will literally just go through examples of NTU versus LNTU, so you can see them back to back and see which one you like more. Okay, take it away.
All right. Hey guys, so as per Professor Spranger's very gracious introduction, my name is Ashish. A lot of you probably met me in office hours. I'm a senior in chem bioengineering, and yeah, you guys are gonna be my game face. This is my first time giving a lecture to an actually decently sized audience. Professor Spranger has assured me that you guys are a very receptive crowd, receptive group of students, that you interact in class, but just as a little bit of incentive. So I've scattered a couple questions throughout the lecture, and I would appreciate feedback and input from you in those moments. So even if you don't know, just like make a reasonably educated guess, because I can't do awkward silences. To incentivize that, if you answer a question that I ask or you ask something insightful, you'll get a Jolly Rancher. I can't attest to my aim, but I'm going to try my best. Another thing, I know the reputation that guest lectures usually have. I've been there. And so if at any point you have a question about something or I'm being unclear, you need something explained in a different way, just tell me to stop, slow down, reiterate. Professor Davis and Professor Springer are also here if I'm unable to handle questions. Okay, without further ado, let's get started. So you guys are chemical engineers. You've had you're working on your third year of schooling at this point. You've seen a lot of acronyms. What do we do whenever we see a new acronym in engineering? We want to define it. Do we have any creative guesses for what the NTU method stands for? Anyone? You guys get candy. Come on, I spent money on this. Any guess? Huh? Very close. Would someone mind passing something to Professor Davis? You can throw that far. See, I study heat transfer, not physics. Or kinematics. Any other guesses? Yes?
Is it like no temperature unknown?
Very creative, very close. Unfortunately, it is not. So NTU actually stands for number of transfer units. So number of transfer units. Okay, sorry, I'm not used to writing on this iPad. Or the number of transfer units method. So back in the 1930s, there was this guy, Ernst Graf Wilhelm Nusselt. I had to call my German friend to learn how to actually pronounce his name. You guys probably know him as Nusselt. So Nusselt, or Nusselt, what he did was he proposed a method of heat exchanger analysis based on this quantity called effectiveness, which we denote as epsilon. So he proposed a method. Also, please let me know if my handwriting is illegible. I've been told that frequently. Of analysis based on. So I'm going to use the shorthand HX to stand for heat exchanger throughout the lecture. And so this quantity epsilon for effectiveness, the formula for that is Q over Q max, where this is an important enough equation that I'm going to box it, and I recommend that you guys do the same. The physical representation of what this is, it's denoting the ratio of the actual heat transfer, and here HT stands for heat transfer, over the maximum possible heat transfer. And so you may say, Ashish, that doesn't make sense. How do you even quantify what the maximum possible heat transfer is? That sounds like a completely hypothetical situation. You're correct. The way you quantify the maximum possible heat transfer is you take the limit as the area of heat transfer goes to infinity. And this is hypothetical. And so last week, or in previous lectures, you went over the delta T log mean method, the log mean temperature difference method. You may say, Ashish, isn't that good enough? Why are you introducing new formulas, new quantities? I promise you that there's a reason for this. We'll get into that later. But this essentially, at its core, it's an alternate to the log mean temperature difference, delta T LM, method. And just as a refresher, that's where you say that the heat transfer Q is equal to the overall heat transfer coefficient U times the area for heat transfer A times the log mean temperature difference. Okay, so before we get further, is everyone with me so far? Sick. Before we get further into the actual math and the nitty-gritty of using the NTU method, what does NTU stand for? Quick check. Nice. I can't throw that much candy, but I appreciate the participation. So we're going to define a couple quantities before we get more into equations. We're going to define something, it's capital C sub H, capital C sub C, and capital C sub R. And these are what we call capacity coefficients. So I'm sure you guys took Gen Chem already, given that it's a degree requirement to pass freshman year and all that. You probably went over this lab where you had this styrofoam cup and you have a certain amount of water inside, and you see how much energy has to add to the cup to raise the temperature of water by 3 Celsius, 3 Kelvin, something like that. Does that ring a bell? Yeah, the heat capacity of water lab? Okay, so you're pretty familiar with the concept of what a heat capacity is. Does anyone care to try and explain that to me? Not capacity coefficient, just heat capacity. Yes?
The amount of energy you have to put into a substance to raise it.
Fantastic. Okay. I'm really sorry if this doesn't work. Nice. Okay. So that's exactly correct. At its core, though, intuitively, I think you can think of heat capacity as a substance's ability to soak up energy, how much energy it can take in before it changes its temperature by a degree. In the case of our heat capacity of water lab in Gen Chem, we're dealing with a static system. The water is just staying in the cup. However, in a heat exchanger, we have fluids flowing all throughout, and we have to take that into consideration. So when dealing with heat exchangers, instead of heat capacities, we deal with something called capacity coefficients, which is the heat capacity of whatever substance we have. H denotes the hot stream in this case, so Cp sub H. And we'll multiply that by the mass flow rate of our stream, m dot sub H. And the units of this are going to be in watts per Kelvin. Similarly, for our cold stream, we can define that C sub C is equal to m dot C times Cp sub C. And so you may say, Ashish, it's the heat exchanger. It makes sense. We have a hot stream. We have a cold stream. What is an R stream? I pulled a sneaky on you. It's not a stream. R actually stands for ratio. This is the capacity coefficient ratio between two quantities that we're going to denote C sub min and C sub max, where our C sub min is the lower of C sub C and C sub H, and C sub max is the higher of the same. Everybody with me so far? Okay. So now that we have a little bit of an understanding of what our capacity coefficients are, we can define, there'll be two situations. In one case, our cold capacity coefficient will be our C sub min, and the other, our hot capacity coefficient will be our C sub min. C sub min is equal to the cold one on the left, and it's the hot on the right. And I want you to just take a quick qualitative glance at these two diagrams and think to yourself for a bit, maybe 5 seconds. What are the differences and similarities you see in between these diagrams? Does anyone want to shout anything out? I'll give you candy. Okay, what about the overall temperature change? Nice. Exactly. Wait, one sec. Nice. Ace that. Okay, that's exactly right. The thing I want you to pay attention to in these two diagrams is the temperature difference of each fluid. So the things that are the same between both, we have our TH coming in at some hot temperature, we have our TCN coming in at some cold temperature, but our outlet temperatures are going to change depending on the conditions of our reactor fluids, or heat exchanger fluids. So here, this quantity here, going across from the left to the right, this is delta TH in this case. This quantity is my delta TC. So in the case where my cold fluid has my minimum capacity coefficient, which fluid undergoes a larger temperature change? Okay, who said that? That was really quiet. Yeah? Did you already get a candy? No? Okay. Breakfast of champions. Okay, and then on the right-hand side, we can do a similar sort of annotation on our diagram. This will be our delta TH. And then this quantity will be our delta TC. And what you can see here is that in both situations, one fluid undergoes a larger temperature change than the other. For the case on the left, it was our cold fluid. For the case on the right, it's our hot fluid. And so, what can you guys say about the properties of the fluid undergoing a greater temperature change? I think I accidentally gave the answer away. I'm going to see if you guys are paying attention. Yes?
The fluid that is has a greater change in temperature has a lower heat capacity.
Fantastic. Nice catch. Oh, sorry. So it's, and sorry, what's your name?
Trent.
As my friend Trent just said, it's the fluid with a smaller capacity coefficient. And so this smaller capacity coefficient, if you recall the definition of our capacity coefficient for any given stream, let's just call it C sub I, it's the mass flow rate of I times the heat capacity of I. So it could be due to lower m dot or heat capacity. And as for the y, this kind of connects to, I'm sorry, I forgot who defined heat capacity for me, but whoever did that did it very well. It's how much energy is required to raise the temperature by, a degree Kelvin. So you can say that less energy is required to create a given, delta T. Okay, so we're engineers. We have to deal with edge cases and corner cases and limits all the time. For the case of these temperature profiles, I want you guys to consider the limit as the area of heat transfer goes to infinity. So what these diagrams show right now, this is across a single length of a heat exchanger. This will be our x-axis from 0 to L, 0 to length L, and this is obviously our temperature axis. And so if we take this length L and we stretch it out till infinity, so our fluids are in contact forever, you can see that for the case on the left, where my cold capacity coefficient is my C sub min, my cold fluid is going to come in and it's going to go all the way up and get almost to THN. The longer and longer my fluids are in contact for, the closer and closer this temperature of the cold outlet fluid is going to get to the hot inlet temperature. So what I'm saying is that as this goes to infinity, this temperature difference is going to shrink further and further and further until eventually, for the case A, the cold outlet temperature is going to approach the hot inlet temperature. Does anyone want to try and make a similar sort of analysis for case B? What happens to the hot outlet temperature as the area of heat transfer goes to infinity? Yes?
It'll approach the cold inlet temperature.
Perfect. And what was your name? Dylan. Nice answer. So T hot outlet will approach T cold inlet. I don't have confidence in my ability to chuck something that far. I don't want to hit Professor Davis' face my bills. All right. Is everyone with me so far? Ready to move on? Sick. Okay, so now let's, actually I feel like I'm losing you guys. Quick check, what does NTU stand for? Oh, that was so sleepy, come on. One more time. Sound excited, guys, this is really cool stuff. Whatever. So now what we want, I feel like you guys are kind of sick of dealing with conceptual stuff. Let's start getting into numbers and equations, our favorite. So what we want a general formula for our heat transfer rate Q, factoring in our effectiveness epsilon. And before we get in, I want you to recall that the definition of effectiveness, epsilon is equal to Q over Q max. And so just like with our temperature profile diagrams, we have to consider two cases. One where our cold fluid has C sub min, and one where our hot fluid has C sub min. So I'm just going to define these equations out. Let me know if I'm going too fast or you guys need more time to write it down. So epsilon is equal to C sub h times the hot inlet temperature minus the hot outlet temperature over C sub c times TC outlet minus TC inlet max. And so when we say T cold outlet minus TC inlet max, this is just delta T max. So let's go through the different terms of this equation, see if we can simplify it down, break it down a little bit. We've defined in this case that C sub min is C sub c. So we can just replace that in. Replace C sub c with C sub min. Delta T max. So what is the hottest temperature we'll have anywhere in our heat exchanger system? Inlet hot. So, I forget, who shouted that out first? Okay. Do you want to raise your hand to let me know who to throw this at? Okay. Well, you can go. Oh, sorry. So it's our hot inlet temperature, THI. And what's the lowest temperature we'll have anywhere in our heat exchanger system? Huh? TCN. You can get another candy. Okay, perfect. And then this top term, C sub h, that's just m dot sub h, Cp sub h. This entire term here, that's just delta T h. This quantity is just Q. You've seen this over and over and over again. And so we can perform a similar sort of analysis for this case here on the right with, so in this case, epsilon is going to be equal to C sub c times TC outlet minus TC inlet over C sub h times T hot inlet minus T hot outlet max. And so we can go through again and replace our terms the same way we did before. In this case, we know that C sub min is C h, so we can just write C sub min there. Same thing, the largest temperature difference you can get is going to be the temperature difference between the hot inlet and the cold inlet fluid. So this will be THI minus TCI. And the top is just once again Q. Does anyone want to tell me anything about these two equations at the very bottom here? Yes? They are the exact same. I saw you raise your hand. I believe that you need the answers. You also. They're the exact same equation. So that means that we can write, same. That means that we can write out a general formula for Q in terms of effectiveness epsilon by doing a little rearranging. Our final equation, so if we rearrange, our final equation is going to be Q is equal to epsilon times C sub min times T hot inlet minus T cold inlet. And again, this equation is important enough that I recommend you box it. What I want you to note is that, this temperature difference here is only between the inlet temperatures. So this delta T is only between inlet T's. That is a hint for this part here. And so now, Professor Spring, do they go on Canvas and do the quiz? Or if you could go on Canvas to answer this free question. You won't get candy for this one, unfortunately.
Okay. Does this sometimes. There we got some.
Sick. Do you care for Jolly Rancher?
Yeah. No, 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 no. Thank you. Nine people have responded.
Okay.
Thought this would have for sure led to this. It's a great question. Say like 30 more seconds. Click in.
All right, guys, this is a class. Okay, we have, how many total? We have 37 respondents, and I'm pretty sure there are more people in this class. Like 20 more seconds, click in with your answers. Keep in mind who writes your assignments and exams and problems.
There we go.
Did anyone fix their?
That looks better.
Okay.
I don't think they can.
Ah.
They're stuck with it.
That's
Okay. Yeah. There you go. 80,
sound about
20.
there. Okay.
Yeah, you can tell them the stats. They always like it.
So we have, oh, interesting.
Interesting.
76% of you picked all of the above. 22% of you picked A. 2% of you picked C. Someone caught my hint. Not entirely, but yeah, great job, guys. So I will say a lot of times, at least in my experience in engineering, if you see a lecturer give an answer with the option all of the above, it's probably going to be all of the above. So the answer here is D. Great job. I wish I had enough candy to give each of you one for participation, but I am a college student and don't have that kind of budget. Let's move on. So, remember how when I started this lecture was about something called the NTU method? Yeah, we're going to get to that now. So, how do we actually determine epsilon? We have this overall equation. We understand what our capacity coefficients are. How do we actually do any math with it? We want to determine a numerical value for our effectiveness epsilon. And to do that, we define this quantity, NTU. What does NTU stand for? I'm this close to giving up, guys. Come on, give me some energy. NTU is defined as this quantity. It's the overall heat transfer coefficient, U, times the area for heat transfer, A, over C sub min. And so we want to observe how the equation is going to change for two different cases. One of countercurrent flow, where if this is my heat transfer surface, I'll have one fluid going in one direction along the surface and the other along the other. And for co-current or parallel flow, both of my fluids are going to be moving in the same direction. Okay, ready for some equations? Very enthusiastic. Let's get started. So for countercurrent flow, we can define epsilon is equal to, this is going to be a really, really long fraction. It'll be 1 minus the exponent. I'm just going to lay these equations up and then wait a couple seconds for you guys to copy it down. Does that sound good? Sick. So it's 1 minus the exponential of negative NTU times 1 minus CR over quantity 1 minus C sub R times exponential of negative NTU 1 minus CR. And this is in your book as equation 22.25. For the case of co-current or parallel flow, we can define epsilon is equal to 1 minus the exponential of negative NTU times 1 plus C sub R over 1 plus C sub R. And this is equation 22.26 in your book. And so I'm going to leave you to jot those down for a bit while I rewrite the rearranged forms of these equations in terms of NTU. So NTU is equal to the natural log, or another fraction, is the natural log of quantity epsilon minus 1 over quantity epsilon times C sub r minus 1 over C sub r minus 1. And then in this case, NTU is another fraction, negative natural log, 1 minus epsilon times 1 plus C sub r over quantity 1 plus C sub r. That's just a rearrangement to get everything in terms of epsilon to solve for NTU instead. I'll give you guys like 15 more seconds to write that down. All right, we good to move on? No? Okay, a couple more seconds. There should be a plus sign. Is my handwriting clear? Are you able to make out the terms? Is there anything I need to clarify? Okay. Okay, people seem to have slowed down their writing. That's okay. I'm going to leave this up for a bit. So these final equations that we get here, I'm not really selling this whole NTU thing to you, huh? These equations are kind of ugly, you know, there's a lot of different factors to consider. But like other things in engineering, rather than closed form solutions, we can often turn to tables and charts and make approximations. That's usually good enough for our purposes. And so these are both figures in your book. I've completely forgotten what the figure number is, but what you can essentially do is once you've figured out what your C ratio is, you can select one of these lines. You could figure out what the number of transfer units is, go up to wherever the value is on the line, and find out what the effectiveness is, and then go forward with your calculations on heat transfer. I just wanted to expose you to it because I'm not sure. Is your example problem going to use these charts?
It'll use a very similar chart.
Okay, so it's going to use a chart like this.
And the one I'll show is C.
Gotcha. So just exposing you to the fact that these exist. Okay, so now it's time for a think, pair, share. I want you to take these equations here that we just discussed, and there's two limits that we're going to consider. One of them you're going to handle, and one of them I am. I want you guys to take 5 minutes? 5 minutes or so, and try and derive what the equations become if you take the limit as C sub r goes to 0. And then I'll take care of the case where CR is equal to 1. I want you to do this for both types of exchangers, with countercurrent and co-current flow. And I'm going to be walking around. If you have any questions, if you ask something insightful, I will give you candy. Ask a question first. For the co-current, yes, or whatever.
Since this is your last meeting.
Good. I was gonna say you can give them until 9:05. I know you have 15 minutes, so we'll do that. Good job. Here, we can go back up to it for a minute. Let's go back up to the equations where we forgot epsilon.
Oh, okay. And you don't have to worry about the case where CR goes to 1. Just derive CR as 0. I'll take care of CR 1.
Oh, this is
Okay, how are we feeling? Does anyone have some sort of answer, some formula? How many people got a final answer? We're gonna go with it. So, does anyone want to shout out for the case of for the case of countercurrent flow, if my capacity coefficient ratio goes to 0, what is my formula for NTU? Does anyone just want to shout it out? Way in the back. Nice. So NTU is equal to negative natural log of 1 minus epsilon. Did anyone solve for it the other way around, where you took the other equation and solved for CR going to 0? No one. Okay. Well, this, you can just rearrange it. Epsilon is equal to 1 minus e to the negative NTU. I'm going to try to throw this. I don't know if it's going to work. Sorry, what's your name, dude? Sam? Okay. Catch it? The question is, can I Okay. Does anyone want to shout out what the formula is for the case of co-current flow? I'm gonna.
Oh, sorry, I didn't get that one yet.
Sorry?
I didn't get that one yet.
Oh, no worries. Did anyone get it? Anyone other? Okay, Aditya. Wait, you already got candy. Aiden.
I got that it was the same as
Exactly. You can have a watermelon. So NTU is equal to negative natural log of 1 minus epsilon, or epsilon is equal to 1 minus e to the negative NTU. And if you guys in the back didn't hear my insightful friend, these equations are exactly the same. Which means that we can then write for all exchangers, if our capacity coefficient ratio, C sub r, tends to 0, then we can just write NTU is equal to the negative natural log of 1 minus epsilon, or epsilon is equal to 1 minus e to the power of negative NTU. Great job on those derivations. I'm not gonna cover the derivation for the case where CR is equal to 1. I'm just going to give you the formula. So if CR is 1, this is saying that the capacity coefficients of our hot and cold fluid are exactly the same. So in that case, NTU, for the case of countercurrent flow, NTU will be equal to epsilon over 1 minus epsilon, or if you could rearrange, epsilon is equal to NTU over 1 plus NTU. And then for the case of parallel flow, we have NTU is equal to the negative natural log of 1 minus 2 epsilon over 2, or epsilon is equal to 1 minus e to the negative 2 NTU over 2. I'll leave you guys like 15 seconds to write that down. Have I lost anyone yet in terms of conceptual understanding, following through so far? Everything's making sense? Nod, shake, any feedback? Okay. Couple thumbs up. All right, are we feeling good to move on? Everyone's written it down? Yes.
I have a quick question. So for the NTU equation for countercurrent, if the denominator is CR minus 1, so wouldn't 1 minus 1 be 0?
That is a fantastic question. I'm going to defer to Professor Springer.
So for the countercurrent flow, the NTU equation, it's CR minus 1, and so the case where CR, if you divide by 0.
There's a special case when CR is equal to 1. So you can't just, it's like a limiting factor. Ashish is going to go through the case where CR is equal to 1 right now.
I already went
You
through
already
it.
did?
Yeah.
Okay.
I didn't go
so
through
you
the
have to
derivation.
use that, it's like that can't go to 0, right? And so you have to use that limiting case that you wrote down underneath it for CR equals 1.
Thank you. Okay. Excuse me. Thank you for the cover on that question, Professor Springer. Let's talk a little bit about why we actually care about this limit as CR goes to 0. You may be upset at me saying, sheesh, we were done doing algebraic exercises back in Calc 1. Why are you making us do this? There's an actual physical reason. So this is not, it's not just a thought experiment or an algebraic exercise, arithmetic exercise. What it does is this limit as CR goes to 0, it encompasses any and all cases in which my C sub max is much greater than my C sub min. So encompasses all cases where C sub max is much greater than C sub min. And so, for example, this could be a case where m dot Cp, so the capacity coefficient for one stream, is much greater than the others. And this could be due to a lower m dot, or Cp, or both. Any of these factors could cause you to have a lower capacity coefficient. And so talk more about the practical applications of this any situation where we have C sub r going to 0. Well, in any case like this, what we're going to have is a temperature change only in one of our fluid streams. The other fluid stream is going to undergo a negligible temperature change. So we'll only have a delta T for one of the streams. And this is typically, if you have streams coming in at different speeds, this is typically going to be the slower stream. So typically, slower stream. That's because you're going to have such a huge difference in terms of your m dot. So if we can write out an energy balance you know that all the energy being lost by one stream is going to be gained by the other. So let's write that out. M dot Cp of your fast stream times your delta T of your fast stream is equal to your M dot Cp of your slow stream times your delta T of your slow stream. And so in my fast stream, I'm going to have a super high M dot. So this term is going to become very big. If the energy transfer that I'm talking about is the same, like I'm transferring the same amount of energy, in order to balance that out, the delta T is going to have to become very small. And so this result is essentially the same as for the case of a single tube heat exchanger with a constant TW. That is important enough that I'm going to write it down. Result is essentially same as for single tube heat exchanger with constant TW. And that's just the fluid on the outside of the shell of the single tube heat exchanger, or tube. That's a lot of words. I'll give you a little bit of time to write that down. And then I want you, while you're writing this down, I want you to think about what other cases you've seen in chemical engineering that has nearly constant TW. I'm going to wait until I see the pencils slow down a little bit. Does anyone have any ideas about what another significant situation has a constant TW? Any ideas? It doesn't have to be correct. Just shout something out. Oh, did I hear something? Latent?
Insulation.
Oh, insulation. Nice. Does that technically count if we don't have two fluids? Yeah, insulation works. Any other ideas? Sorry, would you mind shouting that out? Nice, yes. So condensing steam. So let me write that out. Steam. You both are going to get candy? Sorry, let me just write that example down real quick. So steam condensing on, say, like the outside of a tube. Okay, and so what's special about this situation, this is a very special case of heat transfer. This is a situation where we have a phase change. So phase change. These are also situations where we can use the CR going, use the limit of the CR going to 0. And so you've probably seen a diagram that looks a little bit like this at some point, where this will be Q, this will be T. It's a phase change diagram. So it'll be a solid, it'll rise in temperature. It'll plateau for a bit, it'll go up again, it'll plateau, it'll go up. And this will be our liquid, this will be our gas. And so at the molecular level, excuse me, the differences between different phases is how tightly the molecules are packed together, right? In the solid, you've got this super tightly packed kind of solid lattice of your molecules. In a liquid, they're flowing around each other a little bit more. In a gas, they're completely just whizzing about, taking up as much volume as possible. And so when I'm going between my phase changes, I'm putting energy into this system, into this substance. I'm giving the molecules more and more kinetic energy. And so when I'm going, it'll rise in temperature because the average kinetic energy of the molecules is increasing up until a certain point. At that point, the energy that I'm putting in stops going into increasing the temperature and starts going into changing the phase. And at that point, when the energy starts going into phase change, it no longer changes the temperature. So all energy from heat transfer goes into phase change, not a temp change. Okay, that is, I believe, the end of my lecture. If you guys could take a couple moments to fill out the Canvas participation question, I would greatly appreciate it. If anyone wants candy, I'm going to leave these bags at the front for after class because I don't really want to take it home. Yeah, thank you all so much for listening.
We'll take a break until 9:30.
Without in the corner. I also. Let me steal this. Yeah.